Okay, thanks. So this is based on joint work with my previous advisors, Daniel Kane and Shachar Lovett, and my wonderful collaborator, Gaurav Mahajan. And yeah, I'll be talking about, the title's a little bit cryptic, but maybe characterizing learnability under arbitrary distributional assumptions. Okay. So we just saw in the last talk sort of already a definition of this probably approximately correct learning PAC-Learning model. Let me just very briefly go over it again. So we'll study this general setting of supervised learning, binary classification, just like the last talk, exactly the same. We'll have some set X, think of it as like R to the D, and some arbitrary family H of binary classifiers on X. And personally, I like to think of PAC-Learning as a game played between a learner and an adversary. And the adversary or nature will go first, and they pick some arbitrary distribution D over X, and some hypothesis H in the class that's hidden to the learner. The learner is given sample access, against the pulled labeled samples from this distribution D, a bounded number, and likes to, wants to output a guess for what the underlying hypothesis H is. And the learner wins the game if their output is close with respect to the distribution D in some formalized sense in classification distance. And a class is called PAC-Learnable if there is a winning strategy for the learner to this game. Or slightly more formally, L is called a PAC-Learner if for all epsilon delta greater than 0, the output L of S has error at most epsilon with probability at least 1 minus delta, where error is just the probability that L of S on X is not equal to H of X for the adversary's output, H. Exactly the same definition we saw before, but just to overview things. Okay, so PAC-Learning, traditional PAC-Learning, leads to a really elegant characterization of learning. Right? We have VC dimension. We just saw all these things in the last talk. It's still a very vibrant and beautiful characterization of learning. But sort of this elegance comes at a little bit of a cost. This model is extremely adversarial, and it's often considered too worst case in practice. In particular, the adversary is allowed to choose any sort of contrived arbitrary distribution over the data, and this leads to somewhat contrived lower bounds coming from atomic or sort of weird combinatorial distributions that maybe don't really appear in practice. Okay, so how do we handle this? Well, I've heard one way to handle it in practice is just by ignoring theory, but we're theorists, so maybe let's take a different approach. There are, I think, two sort of natural ways to try to handle this. One is to sort of zoom in and look at specific types of set X that are still fairly general, like R to the D, and specific sets of distributions like Gaussians or things with nice anti-concentration and concentration properties. This is very, very well studied. We have a lot of beautiful theory on this, and it's not going to be the focus of this talk. The other thing you can do is sort of zoom out and generalize the PAC model and study more generally learnability of triples, XHP, where P is some subset of distributions that's known to both the adversary and the learner. So the setting, I won't go through it formally, it's exactly the same. The only difference is now A picks a distribution from this class P. Everything else is exactly the same, epsilon delta, yada yada, so I'm not going to go through it. And the main question, the high-level question is, can we somehow characterize which triples are learnable? Is there some property or dimension or something with respect to P that tells us when a class is learnable? Certainly more things are learnable in this case for smaller P, but can we characterize it? Very little is known in this setting, and mostly what is known is sometimes called the distribution family setting, is negative, unfortunately. And particularly, maybe not all that surprisingly, we actually know that there's not any, at least scale insensitive, nice combinatorial characterization of this model. You can't use VC dimension or something like this, because this just isn't really a combinatorial model when you start allowing arbitrary types of distributions. But nevertheless, maybe we can give some sort of non-combinatorial characterization of learning in SHP. Okay, so what do I mean by this? How do we give sort of non-combinatorial characterizations of learning? Well, even in sort of the distribution-free case, there's still a very useful way to do this. And this is through algorithmic paradigms. We actually saw this a little bit in the last talk in talking about ERM. You can try to prove statements of the following form. A class XHP is learnable if and only if some particular type of algorithm Y succeeds, like empirical risk minimization. In this talk, we'll consider two particular paradigms. One is uniform convergence, which corresponds to ERM, that we were just talking about. And the second is maybe a slightly less studied setting called density estimation that I'll talk about more, but is essentially equivalent to uniform convergence, as we'll see. And let me just make sort of one assumption throughout the rest of the talk, is we'll assume some sort of very obvious necessary condition for learning in this setting, which is that for any fixed distribution D in the class, I want that the triple XHD is assumed to be PAC-learnable. Why? Because if there's some D, more or less where it's not PAC-learnable, the adversary will just pick D and win. So I'm going to assume sort of without loss of generality that each, if the learner knows D, the class is learnable. Okay. happy with that. So I want to now briefly overview these paradigms that we're going to be looking at. I'm sure everybody in the audience is very familiar with uniform convergence. It's like the most basic paradigm in learning theory. So what does the uniform convergence say? It just says, given enough samples from the distribution, labeled samples from some joint distribution, all the empirical errors of hypotheses in H should approach their true error with high probability. Right? Formally, a class is said to satisfy uniform convergence, or UCP, if for all epsilon delta greater than 0, there's some number of samples and epsilon delta, such that for all joint distributions over labeled samples, the probability that your sort of maximum divergence of empirical and true error over the samples is greater than epsilon is less than delta. Right? So we should get sort of true convergence of empirical to true error. And as I said, algorithmically, this corresponds to empirical risk minimization being a working algorithm. You just take n epsilon delta samples and output the lowest error hypothesis, and it'll work under this assumption. Okay, so the second paradigm we're going to look at is density estimation, which is somewhat less common, but I think still a very highly useful paradigm. It's used a lot in semi-supervised and active sort of settings, if people are familiar with these. So what is density estimation? In our setting, it basically corresponds to some sort of natural unsupervised version of the PAC problem, or I guess eponymously learning the marginal from the title of the talk. What's the game? So it's the same setting, but now the adversary will just pick a distribution. They won't pick any hypothesis. And the learner will draw a bounded number of unlabeled samples from this distribution, and they'll try to output a guess L of S, some distribution for D. And when do they win? Well, this better have to do something with the class, right? Because I haven't mentioned the class H yet. So the learner wins if L of S is epsilon close to D with respect to events in the class H. Right? In other words, for all pairs HH prime and H, I want that the distance between H and H prime under my output distribution should be within epsilon of the distance between H and H prime under the real distribution. I haven't written it out here, but this is like exactly learning D in total variation distance with respect to events in the symmetric difference of H and H. Okay, if that didn't track, it doesn't matter. You just want these distance estimates for every pair in the class, essentially. And algorithmically, I've said these sort of correspond to algorithmic paradigms. What does this correspond to? Well, I've made this assumption that each individual class is learnable, right? So I have a learner for the specific class XH L of S, and the claim is that morally, because L of S and D are sort of promised to be close, I can basically just learn XH LS instead of XHD and be done with it. If we have time, we'll sort of formalize this more at the end of the talk. But that's the rough idea. And I want to note, this is very, very closely related to uniform convergence. I haven't sort of written it mathematically in a way that's clear above, but this distance function is exactly the error of H prime under the joint distribution of D labeled by H. Right? So both of these, uniform convergence and density estimation, are basically just paradigms of estimating hypothesis error. They're slightly different. One is from labeled samples and one is from unlabeled samples, but they're very, very similar. Sorry, is there some question? No. Okay. Okay. So why am I talking about these paradigms? Well, this brings us to a seminal and very beautiful characterization of learning in the distribution-free setting, a non-combinatorial characterization of learning, often called the fundamental theorem of statistical learning, at least sort of the right side, which says that a class is PAC-learnable if and only if it satisfies the uniform convergence property. ERM works if and only if it satisfies, has a density estimator, satisfies density estimation. So here's the non-combinatorial characterization of learning. And we might hope that this sort of escapes the known lower bounds of Leshner and Ben David against combinatorial characterizations. So here's a core question. Does the fundamental theorem hold beyond the distribution-free setting? Does it hold under arbitrary distributional assumptions? Okay, maybe some of you know the answer. Because this has been known since before I was born. It turns out the answer is no. Uniform convergence does not hold under distributional assumptions. This is too much to hope for. There's a very simple example due to Benedict and Itai, where they just take X to be the unit interval. They take the class to be just a uniform distribution. There's just a single distribution. And the class is the all ones vector plus the indicator of all finite subsets of X. I won't go in exactly detail why this is learnable but doesn't satisfy uniform convergence, but I claim it's a very easy exercise to show this is learnable in one sample. Basically, if you get a 1, output 1. If you get a 0, output all zeros. But it fails uniform convergence, because if the adversary picks all 1s and you draw any finite sample, you can't tell between one of the sample that you've seen having error 1 or error 0. So there's no uniform convergence in the setting, but it's trivially learnable. Okay, and this is sort of where things stood for 30 or so years. This theorem doesn't hold. Okay, what do we do? I claim that you maybe shouldn't be fully satisfied with this being resolved above, the relation between density estimation and uniform convergence. In particular, it should be clear that uniform convergence is not equivalent to density estimation in the distribution-dependent setting. Why? Well, clearly you can do density estimation here. There's only one distribution. I just output the distribution. So, okay, we sort of haven't solved the density estimation side of this thing. It's still possible that they might be equivalent. And second, there are natural relaxations of uniform convergence that you could ask whether they're equivalent. So here we've only looked basically at the empirical estimator of error, right? Taking a sample and just saying my true error should be close to the empirical estimator. But maybe I can show that learnability is equivalent to just having the existence of some different estimator. Maybe it has to be a different estimator, but there are natural relaxations you could try to look at to show equivalences with learning. So maybe the real question here is there some variant of the fundamental theorem, this type of algorithmic characterization that holds beyond the distribution-free setting? Okay, so now we finally can state the main results. The first of which is a connection between PAC-Learning and density estimation. It turns out, unfortunately, that these are not equal, not exactly equivalent beyond distribution-free, but you can prove that PAC-Learning is sort of tightly characterized as sandwiched between two sort of very closely refined variants of density estimation. On the right-hand side, we have a sufficient but not necessary condition that we call intermediate density estimation, which is basically just a learner that produces good estimates for most events in H with high probability. I'll say something slightly more formal in a second, but maybe we'll end. And the learner should have some knowledge of the set of well-estimated events. Okay, and on the other hand, we have weak density estimation, which is necessary but not sufficient. And this is almost exactly the same, except we drop this requirement of knowledge, that the learner will sort of have good estimates for most things in H, but it can't tell which things it's estimated well. It doesn't know. It turns out that this sort of strictly sandwiches PAC-Learning. And what about uniform convergence or estimators? Where does this come into the picture? Well, it turns out that under this sort of individual learnability assumption, you can prove that density estimation and the existence of a non-empirical uniform estimator are just equivalent. So you might as well sort of just focus on this density estimation picture. Okay, I have like, oh, I guess I'm out of time. So maybe let me just say very quickly, what is it? Let me be slightly more formal about density estimators, and then we'll end. So instead of actually outputting distributions, we're going to output distance estimators. We're going to, we're trying to estimate these distance function between H and H prime. So we're going to output some d hat, and the goal is that on most pairs H prime, the distance estimator on H prime should be close to the true estimate, and you want this to be true for most H and H prime. So what does this formally mean? There's no actual measure on H, so how do you formalize this? We'll say L has an intermediate density estimator if, standard stuff for all epsilon delta greater than 0, distributions in the class. L outputs an estimator d hat such that there is some sample-dependent subset G of sort of well-estimated hypotheses, so that one, sort of with high probability, all of the hypotheses in G have well-estimated distances, and two, for every fixed hypothesis in the class, H is probably in G with high probability. This is how we formalize this notion of density estimation. And notice that sort of the important thing here is that G only depends on the sample, which it means essentially that the learner knows what this class G of well-estimated events is, which allows for sufficiency. Weak density estimation is almost exactly the same. You change literally one letter. G now depends on S and the distribution, which means the learner no longer has access to what G is. And it turns out this is necessary but loses sufficiency as a result. OK, I'm out of time. So I'll just flash open problems and not talk about the proof. But feel free to come talk to me afterwards if you're interested. Thanks.
So Benedict and Itai and Vidyasagar, they had some like necessity and sufficiency conditions based on metric entropy. How does your weaker and stronger density estimation correlate to the?
Yeah, it's a good question. So this condition that I assumed on each individual class is learnable, that is equivalent to uniformly bounded metric entropy. Okay. So I'm really sort of cheating, and throughout this whole thing, I'm already assuming uniformly bounded metric entropy. Okay. Like, this is needed for these results to be true.
I see. Okay.
We sort of start with their work as a base point.
Okay.
There is no, so uniformly bounded metric entropy is not sufficient.
Yeah.
It's sufficient when D is a single distribution, but not, it's false for a general family of
right.
Right. This was written by Dudley, Kulkarni, Richardson, and Zayton. So it's basically a base necessary condition that we're then basing all of our.
But there's a stronger version of that, which is sufficient, I think, of uniformly bounded metric entropy, where. Yeah, we can discuss after.
There's a very strong.
Yeah, there's very strong.
Requires something about the distribution. Yeah. Having an internal point. It's way too strong.
Okay.
It's basically unrelated. It's so strong, it's